Alright, so in this video we are going to talk about net force, and then we're going to start talking about Newton's second law, which is probably one of the most important things we're going to do for the rest of the semester, because the next 2 units heavily depend on you being able to solve second law problems. Okay, so first let's talk about net force. Now we've kind of alluded to net force in the Newton's first law, because Newton's first law says an object at rest remains at rest. And an object in motion remains in motion unless remains in motion at constant velocity. That's the most important part, unless acted upon by a net force. Okay, so what does that mean, net force? Well, specifically, the net force on an object is defined as the sum of all of the forces acting on that object. And by sum, I'm talking about adding. And so what you're literally doing is you're adding up all of the forces acting on the object that you're talking about. Now, that sounds pretty easy, but it's actually more complicated than it sounds, because what you're adding is you're adding up forces, and force is a vector. And adding vectors is actually much more complicated than just adding numbers. And so this isn't a matter of just adding up numbers to get the net force, you're adding vectors. And then you have to take into account the direction and all that. And so that's why we'll spend a lot of time talking about how to do that. Okay, so the net force is the sum of all of the individual forces acting on an object. Because it is not itself a force, it is just the net force. It is not a type of force, so you never put net force on a free body diagram. It is just basically the culmination of all of the forces acting on an object. Okay, you could have 1,000 forces acting on an object, but you would only have one net force. That is the overall sum of all of those forces. Okay, so kind of like we did with kinematics, we're going to start off doing problems in 1 dimension, and we're going to step it up to 2 dimensions. And then in the next unit, we'll do more complicated 2-dimensional problems. Again, force is a vector. The direction matters. Pay attention to the signs of your forces, because you do have to take into account whether a force is acting in the positive or negative direction. Also, pay attention to whether you're talking about forces in the x direction or the y direction. And again, we'll do some examples so you see exactly what that looks like. Okay, so let's start with example 1. Example 1 says, based on the free body diagram shown to the right, describe the motion of this object, and then calculate the net force on this object in both the x and the y direction. Now, looking at this FBD, I see right away that the overall net force is going to be to the right. Okay, because the 6 newtons up and the 6 newtons down, those two forces are going to basically balance each other out. Okay, you also have 20 newtons to the right, 3 newtons to the left, and 20 is more than 3, and so the overall net force is going to be to the right. Now we know, because of the first law, that if the net force on an object is not equal to 0, that object will accelerate. And so what I would say to answer this first question, it says describe the motion of this object, I would simply say this object is accelerating to the right. Now, does that mean the object is moving to the right? No. Remember, acceleration has nothing to do with how fast an object is moving, and it has nothing to do with which way an object is moving. Okay, that would be velocity. Acceleration has to do with how quickly the velocity is changing. Okay, so I know that the object is accelerating to the right, meaning its overall velocity is changing to the right, but I don't know which way it's moving. There's no way to know which way this object is moving without more context in the situation. Okay, so this is the best I can do. This object is accelerating to the right. That's it. Now, how does the net force calculation look? Okay, so this is a very basic calculation, but I want you to see what this looks like. What I'm going to do is I'm going to find the net force in both the x direction and the y direction. So for the net force in the x direction, actually let me do it over here so I have space. Alright, so I'm going to write F net, that's the net force. I'm going to write F net x, and I'm going to do the sum of the forces. But when I say F net x, I'm only going to add up the forces acting in the x direction. So the way I do that is I look at the forces in the x direction. There's only two forces in the x direction. There's 20 newtons to the right, so I write down 20, plus, because remember the net force is the sum of the forces, so I have to add this 3 newtons over here, but look at the direction of this arrow. It's pointing in the negative x direction. So I would say 20 plus negative 3, and that would give me a net force of 17 newtons. The net force in the y direction, I would do the sum of the forces in the y direction. So I have 6 newtons going up plus 6 newtons going down, and that gives me a net force of 0 in the y direction. And if I wanted to, I could write net force in vector component form. I could write that as 17, 0 newtons. Okay, so the net force has an x component to the right, but it has no y component. And that's it. That's how you calculate net force. Pretty simple, right? Okay, so pause there if you need to look at it some more. Okay, so example 2. Example 2 says calculate the net force for the 3 free body diagrams shown to the right. Make sure to indicate whether the net force is in the x direction or the y direction. So again, we're not doing Newton's second law yet. We'll get there in a minute. But Newton's second law has to do with net force, and so it's important that you understand how do you actually calculate net force. Okay, so let's say this is number 1, number 2, and number 3. Okay, so for number 1, I look at this FBD. I say, okay, all of these forces are in the y direction because this is up and this is down. So really, when I go to find the net force, really what I'm finding is F net y. Okay, so because F net x would be 0, there are no x forces, so it would just be 0. There's literally nothing to add. So F net y would be 1200. And notice that's a positive 1200 because it's 1200 newtons up, plus negative 800 from the force of gravity. And it's negative because it's pointing down, which is in the negative y direction. So I would say the net force here is 400 newtons. Remember, force is a vector, and net force is a vector. And this being a positive value means that the net force is acting in the positive y direction. Okay? In other words, this object, based on the free body diagram, has a net force up, and so this object would be accelerating up. Okay, for number 2, I do the same thing. I look at the FBD. I say, oh, well, there's no x forces, so F net x would be equal to 0. I'm not even going to bother writing that. I only care about the y forces because there are no x forces. And so F net y would be equal to a positive 600 plus a negative 800. And that would be equal to negative 200 newtons. Okay, so the net force acting on object number 2 based on the FBD over here is negative 200 newtons. Now, what does that negative sign indicate? Remember, force is a vector, and so that sign indicates direction. That's saying that the net force on this object is going down in the negative y direction, and so this object is accelerating down. Okay, so pause it there, look at number 1, look at number 2, and I want you to try to figure out number 3 on your own. Okay, notice for number 3, based on the free body diagram, you will have to find the net force in both the x and the y direction. Okay, so I want you to pause it here and try to find the net force for object number 3 based on the free body diagram. Okay, so this is what you should get for number 3 based on the free body diagram. Let me erase these other ones. Okay, so number 3, we have an F net x, and we have an F net y, because we have forces both in the x direction and the y direction. So let's start with the x direction. F net x means the net force in the x direction. By the way, this is kind of slightly off topic, but please don't confuse Fn, which is normal force, with F net, which is net force. two completely separate things. Okay, a normal force is the force coming from a surface. The net force is the sum of the forces acting on an object. Okay, two completely different forces. So F net x, I'm adding up all the x forces. I only have one, but notice it's pointing to the left in the negative x direction. And so that would simply be negative 20 newtons. Okay, for F net y, I would do positive 50 from the normal force going up, plus negative 50 from the force of gravity going down. Again, pay attention to the direction, and that would give me a net force of 0. Okay, so this free body diagram, if I were to write the net force on this object in vector component form, would be negative 20, comma 0. Okay. Notice that this is not like using a north, east, south, west coordinate system. This is using like a, the x component is the horizontal direction and the y component is the vertical direction kind of coordinate system. Okay, so in other words, this overall net force is to the left. This object is going to accelerate to the left. Now, does that mean it's moving to the left? No. It just means it's accelerating to the left. Although I will say, if the force of friction is acting to the left, friction always opposes motion. And so we can infer from context that this object is probably moving to the right, which is why friction's moving or is pointing towards the left. Okay, so hopefully you now have a better idea of what is meant by net force. I think we will go ahead and stop the video here. In the next video, we will get into Newton's second law. We'll start off with some more basic problems, and then we'll spend lots of time over the next couple days doing problems with Newton's second law, okay, which again is probably one of the most important things we will do for the next couple months. As always, please let me know if you have any questions, and I'll see you guys in the next video.